Right, so this time I'd like to say a little bit more about the idea of a group as a thing inside set, the category of sets. So, first a few notational points. So last time I just kind of lost it somehow. I should have called this thing eta. The unit I should have called E. Last time I called that E. I should really, you can't see that, but probably a good thing. I called this E last time and it should be called eta. And I called something eta which should really have been called epsilon. So epsilon is supposed to be this sort of terminal map from any set to one object set, the unique such thing called epsilon. So another comment I should make is about this unit axiom. So if you stare at it carefully, then you see there's a bit of a type, an error of type checking. So this is supposed to be the identity. That's a bit harder. Identity on G and the identity on G. They seem to go from different things. So if I just write this out as a commutative diagram, it might become a little more clearer. So what we have is, so we have this isomorphism. G is isomorphic to G cross a point. This is just the thing that you have in sets. It's the obvious isomorphism, and it's from there that we can then apply. Oh, we'll go this side. We do the identity on G. We'll do eta. So we go. Not sure which way around I'm going this square. So we're going G cross star to G cross G, and then we can do mu, and that's just the identity. So this little map here is sort of hidden in this notation, so I should just put that in the notation. So where this is the unit map. Okay, so the next thing I want to comment on is delta. So this is an important bit of structure of the category of sets. Whenever you have a set, you have the diagonal map into the set cross itself, just by the fact that the Cartesian product we're using here is the product in the categorical sense. So what is a product in the categorical sense? To remind you about that. So if we have sort of the categorical motion of the product, categorical product. So if we have a pair of objects, what am I going to call the objects? Let's call them A and B. We have A cross B is a product if it comes equipped with two maps, projection to A and projection to B, pi A and pi B, if we want to call them, give them names, we'll call them pi A and pi B, with the following universal property. So the universal property is that if we have maps, let's call it little a's as elements of the group. So let's call them little map alpha here from X to A, and we have a map beta from X to B. If we have two such of those, then we have a unique map from X down to, this is supposed to be unique, A cross B, such that if we compose that with either projection, oh, I'm sure I've got a bit wonky here, but never mind. If we compose it with either of the projections, then we get the two maps that we first thought of. So given two such maps, we have this. So this is the fact that we have a categorical product. So cross, the Cartesian product is the product in the categorical sense. And so what is delta? So delta is just coming from the kind of the silliest thing you could possibly think of, which is, so if we have, we just take these two maps, alpha and beta, we just take alpha just to be the identity from A to A, and beta to be the identity from A to A, then we have this unique map into A cross A, such that we get the identity. And it's this unique map of this property which is called delta. So delta comes out, the diagonal map delta comes out of the structure of the category of sets. So this is embedded in the category of sets. So I don't have to refer to elements here, which we don't want to do. Don't have to refer to the elements. I just use the universal property of the categorical product to do that. Okay. So that's going to be important in a minute. So what else do I want to say? So another important thing to say is we look at these two things, the associativity and the unit axioms, and I get rid of the, oops, I should have ordered this slightly better. We'll take these two bits of data, satisfying these two bits of axioms as they are. Then what I can do is I can see that this is just the definition of a monoid. So if I just taking associativity and unit gives means that a group is a monoid in set. So remember, a monoid objects or monoids can be defined in any monoidal category. So I guess what I'm saying here is sets is a monoidal category. So this is a monoidal category when it is equipped with the Cartesian product, and the unit object inside that monoidal category is just this terminal set, the one element set. But you knew that already. You knew the group is just a monoid with some other stuff, which is just the inverse, satisfying the inverse property. Right, so we know that a group is a monoid. What you might not know, however, is that every set is a comonoid. So you take any set, any object in the category of sets, and it turns out it's a comonoid. So what's a comonoid? So a comonoid is just the same as a monoid, except you switched everything round. I mean, that's a bit of a silly way of saying it, but that's really what it is. So a comonoid is something. So a comonoid is something with a co-multiplication. So this is S is going to be something with a co-multiplication. Well, not delta, but let's just call it thick delta, just not to confuse it with delta there. So it's from S. So this is a comonoid in sets. Obviously, you can define it in any monoidal category. You just switch everything around. So that's the product going the other way, and we've got a co-unit, which we call epsilon. Let's just call it sort of thick epsilon for a minute, going from S. So it goes to the unit object, satisfying sort of associativity and unit turnaround, satisfying co-associativity and co-unit, which are just, if you draw the commutative diagrams for these two axioms, then you just switch everything around. The multiplication becomes the co-multiplication, and the unit becomes the co-unit. So the point I want to make here is that every object in set is a comonoid in a unique way. So there is only one possible comonoid structure you can put on it, and it is automatically there. And the point is you use exactly these two structure maps. So so I should just write that. I'm just about out of time. I should just write this down. So let me just leave that chap up there. Sets as a monoidal category. So the fact that the cross, just about out of time, is a categorical product means there exists a unique comonoid structure on every set S, and it's given precisely by if I replace G by S. Okay, so that's a good place to start.